I thought I would do the exercises since I didn't do them last video. So I skipped over the examples because these images didn't render in Emacs. So I'm gonna try doing these. So he defines a data type prop. Let's see. Oh. Not and he doesn't define a logical OR. That's weird. But he does do implication. Oh. So yeah, I'm trying to learn this new editor. Var not and imply. Okay. Okay. In order to evaluate a proposition to a logical value, we need to know the value, blah, blah, blah. Okay. Oh. For example, the substitution a false, b true assigns the variable a to false and b to true. Okay. A function that evaluates a proposition given a substitution for its variables can now be defined. Okay, that's a lot of typing. Maybe I should. Okay. Eval of a constant is b. Oh, we've defined it. Oh yeah. So what's next? Not x is, I think. Oh yeah. So then he just translates it. Why does that not work? Couldn't match expected type with actual type. Oh, here. Variable not in scope. What? Oh, because, okay. I'm dumb. And I think we need to, yeah. Okay. Then eval s imply whoa, what is that? Oh, that's just less than or equals. Wow, that's interesting. Less than or equals on booleans is the same as implies. That's strange. Huh. Yeah, I mean, Yeah, so the only time this is false is when the left hand is true and the right hand is false. So, yeah, so makes sense. But I would have never thought of that. Okay, to decide if a proposition is a tautology, we will consider all possible substitutions. Yes, yes. Okay, so vars goes from prop to a list of characters. Vars of a constant is nothing. Var of a constant is nothing. So that's just, a constant is just true. But in my data type, oh, const bool. Oh, I didn't even see that because it's like up there. Huh. Can I not write that like better? No. Whatever. Wait, let's check how he did it. He aligns the pipes underneath it. Yeah. Vars. Vars of variable is x. And then we just do recursive. Like that. Yes. Vars and PQ is vars P plus vars Q. And we can drop the parents. Wait. Okay. Vars apply. There we go. Yatta yatta. Okay, definition of bools. So this generates a list of lists for all possible binary numbers represented as booleans, I think. Int to bin. Okay. We later need to copy that one, I guess. Bools. Int bool. I don't understand any of this, to be honest. Range where range is 0 up to the n minus 1. Make n b's is take n b's. Repeat 0. Con 0 is false. Con 1 is true. And then we are missing that function. So let's go grab it. Into bin. Where are you? This is it. Okay. Why is it complaining? What is this here? What? It's a breakpoint? Let me see. I don't know what happened there. Oh. Lexical error. Oh, these are supposed to be backticks. Like that. Bit. Not in scope type. Constructor of class bit. Oh, it's just an alias. Oh, what the hell? Okay. Type bit is int. All right. Okay. Let's see if we can bools 5. Oh, bools 4 that was, but okay. Bools 4, so that works. So now we need to find our thing again. Oh, I could have just done the last. Wait, what? Where are we? Okay. Yeah. To decide if a proposition is a tautology. Okay, yeah, we're back where we were. Okay, bools. There is, however, a simpler way to define bools. What? I didn't have to copy all of that. Okay. Oh. Okay, and let's delete. Oh, okay. Using bools, it is now straightforward to find a function that generates all possible substitutions. All right. Where vs rm dups. Okay, let's do it in a new tab this time. Rm dups. Oh. Let's see if this works. Substs. You should, let's try var x. Yeah, it works. Okay. Now, what is this stuff also? Oh yeah, we're in the wrong chapter. Substs. Okay, abstract machine. Oh wait, he hasn't done the actual tautology thing yet. Okay, finally, we define a function. Okay. Oh. Is taught var x. This should be false, right? Oh. Boom. But if we do is taught, I mean, there's no or. I wonder why he. Strange. Is taught imp. Impl? Was it impl? Imply const true, or no, this should be a variable var a true. I think that's a tautology. Typo. Imply var a true. And this should be const true. Yeah. Okay. Maybe I shouldn't have done all that because I was just copying over code basically. Let's go to the exercises. In a similar manner to the function add, define a recursive multiplication function mult for the recursive type of natural numbers. Wait, so net is not defined. So I need to go back. Oh. Net. Okay. Data net. Here. Oops, my battery's gonna die. Okay, and then go back to the exercises. Oh, we should have copied over add as well. Data net. Add. And then we need to add those. Oh, wait. However, using recursion. Yeah, okay, so I should have copied this one. Oh. There we go. And define a function mult. No. Exercises. In a similar manner to the function add, define a recursive multiplication function mult for the recursive type of natural numbers. Hint, make use of add in your definition. Okay. Let's try and run this. Add suck of 0 to 0. Okay. How does that work? Again, deriving? No. Nope. Here, if you wish to try out such examples, the phrase deriving show must be added. So why doesn't it work? Hey, that was surprisingly hard. Why can I not? I thought, oh, it has to be indented. And then these, oh, yeah. Okay. So a definition for mul or molt. Oh my God. How am I gonna find this abstract machine? Oh, exercises here. Molt. Okay. Net to net to net. Molt 0 n is 0. Molt suck of 0 n is n. And then I think molt of m and n is add n to molt. Oh, we should use pattern matching to unwrap that value, I think. Wait. So a successor of something, then we add n to molt mn. Is that right? Maybe we should let the left one go down. I don't know. Instead of the right one. Molt 3x4. No instance for numnet. Oh yeah. Wait. So we should definitely do the left one. Suck m. Wait. N. I mean, I think that works, right? Let's see. Nope. No instance for numnet. Oh. I can't just call it with that. Yeah. Okay, I see the problem now. Multiply successor of 0. So that is 2, right? And then multiply 2 by 3. Suck 0. Boom. And then it gave us, so 2 times 3 is 1, 2, 3, 4, 5, 6. So it works. That's nice. Although not included in Appendix B, the standard prelude defines data ordering together with a function compare that decides if one value in an order type is less than or equal to or greater than another value. Using this function, redefine the function occurs for search trees. Why is this new definition more efficient than the original version? Let's see. Occurs. Oh yeah. Okay, so it's saying although not included, the standard prelude defines ordering together with compare. Redefine the function occurs. for search trees. So I think what that means is we can assume that the tree is sorted, yeah. But okay. Let's see. Occurs new. Maybe I shouldn't have renamed it. Ord a tree of A's bool. And then we can say occurs new of a leaf is only true if x is equal to y. That stays the same. Then occurs x node t1 y t2 is. Now it gets interesting, right? If y is less than, so I think we're gonna do this thing, cards, I think it's called. If x is less than y, if they're equal, if x is equal to y, then we return true. If x is less than y, then it is occurs new. Oh yeah, and this should be new. Okay. Occurs new in the left branch. X. If x is greater than y, or here we can just do otherwise, I think. Oh. Otherwise is occurs new xt2. Bam. So what did we have? So that one is not a search tree, or is it? No, because 3 is greater than 1, for example. So 1, 4, 7. And let's make this one. It's kind of hard to visualize it if it's like written down as a. So I think this should be 5, and then here the middle is 7, and here we have 6. Oh. And then here we have 8. That's the search string. Occurs new. Does 5 occur in T? Oh wait, I should reload. True. Occurs new. 3 in T. False. Okay, so I think we solved it. Why is this new definition more efficient? We only check down one path of the tree instead of the whole tree. Consider the following type of binary trees. Let us say that such a tree is balanced if the number of leaves in the left and right subtree of every node differs by at most 1, with leaves themselves being trivially balanced. Define a function balanced that decides if a binary tree is balanced or not. Hint, first define a function that returns the number of leaves in a tree. Okay. Okay, I think we already have that. Oh. That's the same, right? Oh. He has no, the nodes have no values. Okay. How are we? Maybe we should call that a leaf tree. Multiple declarations of node. The constructors need to have a leaf node and a leaf. Multiple declarations of leaf? No, dude. Read again. Okay, there we go. Okay, so we have so now first he says define a function that counts the number of leaves. So count leaves takes a leaf tree and returns an int. Count leaves of a leaf is 1. Right. Here we do need braces or parents. Expecting one more argument to leaf tree. But this is a type definition. Leaf tree. Why does that not work? Let's take a look at nat, for example. So, for example, in nat you have okay, I see what's wrong. Like this? No. Oh no, that's the definition he gave us, right? Data tree A. I'm really curious what I did wrong. Because, for example, with isn't this the same as the add function, for example? You have a constructor called suck. But suck is always okay, I see what's happening here. Wait, does he give us the no balanced tree A to bool? Okay, so we definitely do need the A there, but then why does this not work? Couldn't match expected type leaf tree A with actual type tree. This is a leaf. Okay. And now count leaves of leaf node AB is count leaves A plus count leaves B. Oh, and we can drop the brackets. Oh. Count leaves of T. Yeah, that's not a tree. A leaf tree. That's a tree. Data leaf tree. Okay, let's see. Leaf tree. No, leaf node. Leaf node. Maybe we can just. Oh no, we cannot. Leaf node. Leaf 3. Leaf 4. Oh, and let's here do leaf 5. What? Oh yeah. Maybe we leaf tree unbalanced. That's like a Java name, too long. There we go. Reload. Count leaves. Leaf tree unbalanced. 3 leaves. That's correct, sir. And now he's saying, let us say that a tree is balanced if the number of leaves in the left and right hand subtree of every node differs by at most 1. Okay, so he's basically just given it to us. Data, oh no, we need to define a function. Is balanced, takes a leaf tree A and returns a boolean. Is balanced, let's see. If the number of leaves in the left and right subtree of every node differs by at most 1. So is balanced of a leaf is true, I think. Oh my God. Okay. Is balanced, because here there are no subtrees, so therefore the difference, therefore the condition is implies vacuously, right? So now we have if balanced leaf node AB is equal to count leaves, but does that really work? I don't know. I'm just like transcribing his definition into Haskell, but I'm thinking like, is that really true? Let's do that in a where clause. So is balanced AB if leaf difference smaller than or equal to 1, where left leaves is count leaves A, right leaves is count leaves B, leaf difference is there a abs function in yes there is. Abs left leaves minus right leaves. There we go. So I'm thinking this is balanced because the difference is 1, right? So let's try that. Is balanced LTU true. Oh yeah, and we called it unbalanced because I thought, okay. So this is LT not balanced. Now leaf tree, oh wait, no, that is balanced. Leaf tree balanced. Now we do leaf tree unbalanced. Leaf node, leaf node, leaf node, leaf 1, leaf 2, leaf 3, leaf 4. Oh my God. that's correct. Oh no, it's saying it's not. Wait, what is this here? Parse error, possibly incorrect indentation. Okay. So this closes that. This closes that. What does this say here? Couldn't match expected type with actual type. Did we miss something? So, oh yeah, I passed in 3 leaves. Oh. How can I, okay. Oh. This is just the same thing as I did last time, no? I don't really know. Oh, you should reload. Is balanced LTB? Is balanced LTU? Or couldn't match expected type. I mean, there's only 2 constructors. I don't understand. Probable cause. LTU is applied to too few arguments. What? Oh. See, that is like one thing that I think currying is not very good for, because you can just have half applied functions and they pass the syntax checking. I mean, they pass the type check until you start to use them. I mean, I don't know. It's just is balanced LTU false. Okay, so I think our function works. Define a function balance that converts a non-empty list into a balanced tree. Hint, first define a function that splits a list into 2 halves whose length differs by at most 1. Okay. So first we need to make a split function. Okay, split does not exist. It takes a list of A's and returns a pair of lists of A's, I think. Or maybe we could make 2 functions, one that returns the left half and one that returns the right half. I don't know. Let's do that actually. Split left. Split left. Okay, now I need to think a little bit. Isn't there a function take in Haskell? So take 5 or take 2 of 1, 2, 3, or I could use range here. Okay, so take. Okay, so split left is basically just take divided by the length of the list divided by 2, right? So split left of a function of a list L is take. Wait, is that? Oh. Take length of L div 2 redundant bracket. Okay. Oh. split left of 1 up to 7, 1, 2, 3. And then the right hand is 4, 5, 6, 7. So I'm thinking we should. Okay, let's just try writing split right. Split right. Split right. L is. Now we could do this maybe with. Okay, never mind. I was thinking of like reversing the list and stuff. Couldn't match expected type with actual type, A to A. So they have the exact same type signature. Oh, it just compiles. And this language server stuff, I don't know, only works like half the time. Yes, okay. So we have a splitting function. Now what did he say? Oh. Define a function balance that tree that converts a non-empty list into a balanced tree. Hint, first define a function that splits. Okay, so we're gonna recurse on the two halves, I suppose. Balance, it takes a leaf tree of type A and it returns a leaf tree. Or wait, it takes a list, non-empty list, yeah. Balance. Is he like doing the build up to writing word heap sort, maybe? Balance. Let's see here. So I think split right of a singleton. Yes, that works. And then, okay. And split right on the empty list. What does that do? Okay. Split left of the empty list. Very nice. Balance. L is balance. Okay. We need to have a base case, right? So I think the empty list is we cannot have an empty node. Okay, so if people pass in an empty list, then it crashes, I think. And otherwise it's a leaf. Okay, now balance. Okay. Balance left. Oh yeah, this needs to be a leaf node. Balance left, balance right. Where left is split left L. What? Why did it do that? Okay. Okay, I think that worked. The only thing is I didn't make it showable. Whoa, that's pretty cool. Like, imagine writing this in C or something. It would be way harder. Or in Python even. Okay, given the type declaration, expr. Okay, so how many more? There's 1, 2, 3, 4, 5. There's 5 more exercises. Yeah, I think I'm gonna end it off here.